we have. Then I will proceed with static RAM and then dynamic RAM. Then ROM design, read-only memory design. Then the decoders we use for ROM. Then flash storage and content addressable memory. This is my agenda. So to brief about the memory classification, we can just see. No, in general, we can classify the memory into two types. One is volatile and non-volatile. So volatile means as long as the power supply, as long as we are giving the power supply, we can access the data. We can read or we can write the data from the memory or into the memory. It can be for 10 years. It can be for 10 seconds. How long we are giving the power? How long we are energizing the circuit, the memory circuit or the memory cell? We will be having the memory. We will be having the data stored in the memory. And the other type, which is non-volatile, even though we are turning off the power supply, the memory will be there. So these days we have flash memories, we have SSDs, I mean external hard disk we have. So everything comes under these categories. That is non-volatile memory. And in non-volatile memory, again we have two categories. One is read-write memory. So as many times we can erase the data which is written into the memory, and we can read it. That is read-write memory. We have three major classifications. Anyway, EEPROM, EEPROM. Those are all that is about to extinct from our VLSI perspective. But anyway, we have EEPROM, E2PROM, flash memories we have. Then read-only memory, it is mask programmed. Programmable, we call that as PROM. So once it is once the data is written, once it is programmed, then we cannot write for the lifetime. And coming again to the volatile, it is read-write. We do not have any concept of read-only memory in volatile. So again, we have two classifications. One is random access and non-random access. So the examples for random access are SRAM and DRAM. One is static and another one is dynamic. And non-random access, what is the meaning of random access and non-random access? Random access means, see, for example, we want to write a data into the address line, say 4235H. We can read as well as we can write. But in the non-random access, it is not like that. So the examples are we have first in, first out, last in, first out. Even we can consider the shift register, because in shift register we are putting the data into one side and we are taking the data outside, and we have to go by the order in which order we are giving the data. The same order we are going to take the data out. But in random access, it is not the case. As the name itself, that is how the nomenclature it comes. Random access means you can access any memory by giving the address. We don't want to start with 0000H. It is not like that. We can randomly we can read and randomly we can write. So that's what random access. So with this basic memory classification, I move on. So to know about the definition, so we have to worry about when we are dealing with memory design, we have to worry about three lines of data. Yes, sir. Screen is not visible. Now it is visible. No. Okay, 1 second. Now, process, is my screen visible? Okay. So that's what. So in semiconductor classifications, as I said, we have volatile and non-volatile types, and in volatile we have random access and non-random access. Whether in non-volatile we have read-write memory and read-only memory. So with this introduction, we move on to the memory timings, because see, whenever we are writing the data and we are reading the data, see, writing means we are putting the data into the memory cell. Reading means whatever data we have in the memory cell, we have to read it. So for that, we have to understand a certain memory timing. So we call that as a read cycle and read access time and the write access time. Say, for example, when we are dealing with the read access time, say we will be giving a pulse. So to read the data, we will be giving the pulse, and before giving the pulse or after giving the pulse, say we are putting the data. We are putting the data in the data, data bus. We call it as data bus. So that data, the process takes some time. So some minimum amount of time it will take to settle the data. I mean, we can call it as the valid data. When we can call it as the valid data, so it settles, the complete data settles on the data bus. We call it as read access. So the time between the read pulse, the time between the read pulse and when the data is ready to be accessed, when the data is ready to be read, we call that as a read access. Usually this read access time must be minimum. See, if the read access time is larger, the meaning is we take more time to read the data available in the memory cell. So usually what we should have is read access time must be lesser. That means the data should be readily available in the database. When we are able to read the data from the database, it should be readily available. So we call that as a read access. Similarly, for the write cycle also, we have a thing. But see, in read cycle, so we have to settle the data. We have to settle the data in the database after the read pulse. Say here we have the read pulse. After the read pulse, we are making the data to be available in the database. So that time duration we call it as read access. But whether you go to the write access, it is not the same. Why? Because for reading, we are putting the data from the memory to the database. Whereas for the writing, it is not like that. For writing, data need to be available in the database before we are giving the write pulse. So here we are giving the write pulse, and when the data is considered to be written, so see our data is available in the database. So when we are giving the write access, the data from the database is need to be stored in the memory cell. Right, that duration after providing the write access, when the data is stored in the memory cell, we consider that duration, which is write access. And so this is read access and write access. For read access, data should be put in the database after the read pulse. Right, so you can see here, after the read pulse, we are putting the data in the database. This is one point. Second one, for the write access, data should be readily available in the database before we are giving the pulse. So this is very important in the memory timing. When we are defining this read access and write access, we should always remember the data should be available after the read pulse. Similarly, the data should be available in the database before the write pulse. So now we can understand the difference between read access and write access, and the entire cycle. Say the duration from one read pulse to the other read pulse, we call it as read cycle. Similarly, one write pulse to the other write pulse, we call that as the write cycle. I think you're clear about this memory timings and the classification. Now we move on to the memory architecture. So now how the memory will be stored? See, the memory will be stored like it can be, bytes. So here I have shown the words. Say we have word 0, word means 16 bits. So in general, it will be 16 bits. Even if we have, double words like that also, we can have bytes also. We can have it means 8 bit. Word means 16 bit. A double word means 32 bits. Like that we can have. So how we are accessing it? So we will be accessing every word by using a select lines. So we will be having for example, if we are having 16 words, if we assume that it is a 16 words, we need 16 select lines. So for selecting each word, because what we need to do, we need to access the word cell to access all the 16 bits. Say in a word we have 16 bits. To access the cell, we need to access the entire word. So we need to activate a select line. For example, here, if we need to activate this word, we need to use the select line S3. Say it is S3. We have to select that pulse need to be given to energize the word. That means for reading as well as for writing. Say, for example, if we are dealing with one megabyte of words, again we have to be one megabyte of words. I mean the select lines. So that is actually a disadvantage. See, we have 16 words. For selecting any one word from the 16 words, we have to give one select line. Similarly, for 1 megabyte, we have to give 1 megabyte select lines. But that is the disadvantage. Since we are increasing the number of select lines, that is the disadvantage. That is why what we are going for decoder circuits. Say what the decoder will do based on minimum number of input signals, it can, any one will be selected. See, we have to very carefully understand any one of the select line will be selected, not two. That is the function of decoder. Decoder, any one of the select line will be energized or will be activated, we can say. So for what we are activating? For accessing a memory word, for accessing a memory word. So here what is the problem again? So here, see, we have word, we have m bits of word, we have select lines, and we will be having a problem of aspect ratio. See, number of, again we are having we have only 16 bits, when we talk about horizontally, we have word by word, and each word has of 16 bits. And you see in the other side, I mean in the vertical side, we have a decoder. And but anyway, from the decoder, what we need, for example, if we have 16 words, we should be having 16 lines, 16 select lines. All right, so we will be having a problem of aspect ratio, or here the height will be greater than width. So we know what will happen in a circuit. I'm not talking about the height and width of a transistor, I'm talking about the height and width of the memory cell. So again, here we will be having a problem of aspect ratio. We don't want this, because we considering the power consumption, considering the area utilization, considering the delay, what we are going for memory, I mean 2D architecture of for memory. So in 2D architecture, what we will be having, you put, instead of, say here, for select lines alone, we are putting the decoder. All right, for select line alone, we are putting the decoder. But in the 2D, or we can call it a structured memory architecture. In structured memory architecture, you put decoder for row, decoder for column. So what will be done? So row decoder will be used. See, row decoder will be used for selecting a complete word. Selecting a complete word means energizing a complete word. See, that doesn't mean the other cells, other words are not entirely, not powered. It is not like that. So during the first access, say during the first cycle, I am accessing a third word. During the second access, I may access the other words. So accordingly, it will be getting, accordingly the words will be getting energized. Accordingly, the word, like the entire word line will be getting selected. Okay, now the word will be selected. How the bits will be selected? So bits will be selected by using a column decoder. The same, I mean, same type of decoder, based on based on what lines, how many lines you need. So appropriate to select the appropriate, say the appropriate word will be selected by the row decoder. All right. Similarly, appropriate bit will be selected by what? Column decoder. So one is for what? One is for word. One is for selecting the bit. Say, for example, here we have an, see, the aspect ratio seems good. See, considering column decoder for bitwise, considering row decoder for word-wise, aspect ratio is better than the 1D memory architecture. But again, we have a problem when we have when we have more number of bit lines, because as I already said, here we have taken an example of single word, but that can be a double word also. That can be double word also. That can be stack of words also. More than double also, we may have. During that time, again, the same problem will occur, because we have we should have that much number of column decoder select lines we must have. Okay, and what is the use of the sense amplifiers? As I said, the other words and other bits is not completely powered off, but it will be powered. So during that power, as we are dealing with the static circuit, these static circuits will be always will be having, rail to rail swing we will be having. See, during pre-charge or after the pre-charge, we may have swing between 0 to VDD. And also we will not get higher. So during read operation, I believe during read operation, we may do not want to power, or do not want to energize all the words and all the bits. So in that case, what we will be having, a swing. 0 to VDD, we will be having a swing. And what bit line you are selecting, that will not be a full VDD. We will not expect very minimum to maximum swing, but rather we will be having around, for example, instead of 5 volts, we may get 4.75, like that we will be getting. So to avoid that, we go for drivers or sense amplifiers. What the sense amplifiers will do, it will take the bit line, and from the bit line, it will amplify the signal, and it will amplify the voltage, and it is simple. So as I said, here also we may have a problem of what the rail to rail swing we may have, and aspect ratio is better when number of words is less. If number of words are stacked, to the side by like parallel of the existing word, again we will be having the same problem, the aspect ratio problem. That is why we are going for 3D design. 3D design means we call it as hierarchical memory architecture. In hierarchical memory architecture, instead of having row address, I mean row decoder and column decoder, we may also have block address. So now the address is divided into, see in the previous case in 2D, say I'll go before to the 1D. In 1D, what we are doing, we are having a decoder. We are having a decoder to select only the word. Right, this is 1D. And in 2D, we use two type of decoders. One is for selecting the words, another one is for selecting the bits. Again, we have a problem. In 1D, we have a problem, aspect ratio problem. In 2D also, we will have aspect ratio. See, it is better than 1D. But when you increase number of words, again, we will be having what? We will be having the aspect ratio problem. So to avoid that, we are going for what? We are going for hierarchical memory architecture. In 1D memory architecture, the address bits are divided into only one, that is for only row. In 2D, the address bits are divided into row and column. Whereas in 3D, that means the hierarchical memory architecture, the address rows are divided into three categories. One is for row address, one is for column address, one is for block address. So here, how it is activated? So first, initially the block address will be selected. So it is like a select line only. So it will select a complete block. So we'll be having n number of blocks. Out of n number of blocks, we are going to select only one block. See here, what we are using, we are, this is especially for power saving. Say we are not talking about, bits of memory. Say we are having a RAM, we are having, in GBs. In GBs, we are talking. So we divide the entire thing into blocks, block by block. So you address only one block. So that block alone energized. And by using row address and column address, by using the row address, by using the column address, we can select the word, we can select the bit in a block. So this is during a first cycle. Maybe in the second cycle, another block address may come, right? So that again here, that doesn't mean all the blocks are not powered at all. It is not like that. All the blocks will be powered based on what address you give, based on which memory you are accessing, based on to which memory you are writing the data, or from which memory you are reading the data. So what are the advantages here? We have the shorter wires within the blocks, because the parasitic capacitance and parasitic resistance of the wiring plays a major role in delay as well as. So when once it plays a major role in delay, again it reflects on dynamic power consumption and everything so on. So here, when you go block by block, what is the advantage? We use shorter wires within the blocks. That is one advantage. Another one advantage, you address not all the blocks at the same time. You address block by block. During each cycle, you address one block. Able to understand this? So now getting into the in depth of hierarchical memory architecture. So what we have. So as I said, we will be having, you see the previous hierarchical memory architecture. So here we are selecting the blocks, and in the block you select the word, and in the word you select the bit. This is what we are doing. So how it is being done? It is being done by three different lines. One is global word line. So the global word line is responsible for all the blocks, and in all the blocks we are divided into subglobal word lines that carries to one set of blocks. Say for example, we are having, let us assume we are having some 100 blocks. Out of 100 blocks, we are dividing into 10 blocks. So first 10 blocks, that comes under one subglobal. Next 10 blocks, that, see, it is not tens and hundreds, it will be in thousands and 10,000s for easy understanding and telling. So here we will be having first 10 blocks, then second 10 blocks, then third 10 blocks. That's how it will be designed. That's how it will be there. So here we are going to access what? Here we are going to access one memory cell. So how we are accessing? By using block group select, we can access. So when this will be activated, because of this AND gate, this will be getting one. So when both are one, this will be getting one. So this is going to activate based on the column select. So that memory cell alone will be activated. So this is how it is packed. So block 1, block 0, block 1, block 2, up to block n-1. Since we start with 0, it comes to n-1. This is all about the hierarchical memory architecture. So okay, next one is 60 SRAM, 6 transistor SRAM. Before getting into this, I will just recap what are the things we have seen. So we have started from the memory classification. There we have seen volatile, non-volatile memories, random access and non-random access under volatile memories, read-write memory and read-only memory in non-volatile access. These are things we have seen. Then we have seen two things. One is read access and write access. The difference between read access and the difference, the read access and write access. Then we have seen the memory architecture, one-dimensional memory architecture. We call it as simple memory architecture, in which the address we give is only for the decoder. That is to select only the word lines. Bit lines will not be selected particularly. All the bits will be selected. And in array structure, which is 2D, here we select words as well as we select the bits. So individual memory cell can be picked by giving appropriate select lines in the row decoder and appropriate select lines in the column decoder. We can pick exactly one cell. That is advantage. But here again, when number of words is higher, again the aspect ratio will come. So that is why we are going for hierarchical memory architecture, in which the address is divided into 3 categories: row address, column address, block address. So we don't want to activate, we don't want to energize all the blocks at a time. So we are going for selecting a block, and in the block selecting a word, and in the word selecting a bit. So this is how hierarchical memory architecture works. So now we will discuss about 6T RAM. So why we call it a 6T RAM? Because it consists of 6 transistors. Of course, 6 transistors, out of which 4 transistors are NMOS and 2 transistors are PMOS. You can see, first we will see the write operation. And coming to the design, what we will be having is, we will be having a cross-coupled devices. You can see here we have a PMOS, here we have a NMOS. So you can see N1, N2, N3, N4 are the NMOS, and the P1 and P2 are the PMOS. And we will be having the bit lines, bit line and bit bar line we will be having. Since we are talking about the static design, we will be having bit and bit bar line, and we have a word line. So word is for selecting the word, bit is for selecting the bit. See, this is one cell, right? This is one cell of memory. One cell contains how many transistors? Contains 6 transistors. So is this energy efficient? No, certainly not. This is not energy efficient. But see, we have to talk about the advantages also. We will come to that. So now we have to write it. So we have to write means, so from where you will write? We have to write from the bit line. So whatever data we are putting in the bit line, that should be stored here in the A and A bar. This is A and A bar. See, you see the connection. This is cross coupled. Say we have, so whatever this point carries, whether it is VDD or low or high, that will be over here also. So accordingly, it will turn on or it will turn off the N1 and N3 transistors. But anyway, we are not going to discuss anything about N1 and N3 in write cycle. Why means, say for example, if you are having A as 0, A node as 0 initially, we want to store 1 into that. So for that, what we are going to do, we are going to put 1 in bit and we are going to put 0 in bit bar. Before that, what is happening inside? Before that, let us consider A is 0. So if A is 0, what happens to A bar B? A bar B will be 1. So if it is 0 here, what will be happening to N3? N3 will be turned off. Am I right? N3 will be turned off because A node is 0. At the same time, what about this PMOS? P2 will be turned on. Right, P2 will be turned on. So how the connections is made? See, this is connected to plus VDD. So from this plus VDD, A bar will be 1. This is how A bar is 1. You're able to understand, which is controlled by what? Which is controlled by this A which is 0. Since it is 0 here, this N3 will be turned off, P2 will be turned on. That means this node is pulled up to VDD. That means 1. So A is 0, A bar is 1. Similarly, you see, before giving the word line, N2 and N4 will both be turned off. So this is separate. This is not connected with the bit lines and word lines. All right. This is 0. So N3 is turned off. P2 is turned on. So A bar B is 1. So if this is 1, where it is attached? This is attached to N1. Right. So N1 will be turned on. P1 will be turned off. So what is the meaning? There is no connection between this node A to this VDD. Whereas this node A is now connected to ground. It is pulled down to ground. Why? Because of this transistor, N1 transistor. So this is how it will be. This is how it will be before we are giving any signal. Now what I'm going to do, I'm going to make A as 1. So for that, what I need to do, first I have to give the word line. See, that is the first activity. In any memory cell, word should be enabled. Then only the entire word will be enabled. Out of which then we have to go for the cells. I mean individual bits. So now I put the word signal as on, and I put the word signal as on and bit signal as 1. Bit signal as 1, bit bar signal as 0. So opposite, 0. So now what will happen? Say if I put word bit as 1, N2 will be activated. N4 will be activated. That means N2 and N4 will be turned on. All right. If N2 and N4 will be turned on, you see in bit bar we are giving 1. Say this is on. So this will go. I mean this 1 will be here. In this A bar B, 1 will be here. And because of that, what will happen? N1 will be already in the turned off position, right? So now what it will do, it will make this A bar B to go to 0. How it is making, how we are making this A bar B to pull it to 0? Because as soon as we are putting the bit line as 1 and already word is activated, so this is activated. So when this is 1 here, this will become 1. A will become 1. Once A is becoming 1, what will happen to this transistor? N3 will be turned on. At the same time, P2 will be turned off. P2, see here, it is cross coupled. So what we need to do is, here sizing is very, we have to do it very carefully, because N4 must be, enough, enough strength to make this VDD to pull to 0, because it is on. But when we put 1 here, we have to turn it off, since it is directly connected to, the VDD is directly connected to the A bar B node. So now what has to be done? This N4 is good enough to pull this node to 0. That is why you can see in the timing. So A bar B is 1, and initially when I put the word line and when I put the bit line, so word line is the first activity, bit bar is the second activity, and third activity is making this A bar B to 0. You can see making this A bar B to 0. So when this becoming 0, when A bar B is becoming 0, I mean A bar is becoming 0, what will happen to N1? N1 will be turned off. N1 will be turned off. That means A will never be ground, because when the N1 is turned off, P1 will be turned on. So A will be pulled to what? A will be pulled to 1. A node will be pulled to 1. That is why you can see A will be pulled to 1. So how we can make this? How we can make this? See, now, as I said, during the write operation, we are not worrying about N1 and N3, because during the write operation, it will be turned off. Right? N1 will be turned off. N3 will be turned on. If N3 is turned on, what will happen to A bar B? A bar B will become 0, because it is directly connected to the ground now, due to the path of N3. N3 will be on, so that will make a path between this A bar B and the ground. So now what we have? We have A bar B will be going to 0. A will be turned on. A will be going from 0 to 1. That is, so how it is going to, since A is, see, the thing is, A is connected to 0 with this N1 transistor. We are making this N1 transistor off and P1 transistor on, right, with the help of A bar B. So you can see that is the beauty of this cross-coupled circuit. See, at one time, either N1 or N3 will be turned on or turned off. Similarly, P1 and P2, either one transistor will be turned on and turned off. Right. So because of this feedback, see, this act as a feedback inverter, right? So this has to be overcome. That is a concept, lying under a right operation of 60. I hope everyone is clear with this. So now we get into the read operation. So for read operation, what we have, see, in the write operation, what we are going to do, we are putting word bit as 1 to enable N2 and N4 transistor. And then we go for bit. So whatever we are going to do, for example, we need to put 1 into the cell. I make this bit line as 1, bit bar as 0. This is happening in what? Write operation. But in read operation, I am not going to do that, because I am going to read the data from the cell. I mean, from the A, I has to be read to the bit line. So for that, what see, for reading operation, always in the bit lines, we need to precharge. Precharge means it is like a pulse. It is like a single pulse. So if I give a single pulse, I mean, at the same time I have to give, see, bit and bit bar, at the same time I have to give the precharge, a single pulse. So if I give the single pulse, what will happen? You see, if I give the single pulse, say single pulse, and I am removing the pulse. Now this, this bit line and bit bar line will be hanging. We cannot say it is 0, or we cannot say it is VDD. It will be hanging, right? So now you turn on the word line. Now when the word line is turned on, for example, if here the data is 0, let us assume here the data is 0. Now you turn on the word line. If I turn on the word line here, what has to be done? N2 should be turned on and N4 should be turned on. If N2 is turning on, let us assume A is 0, so N2 is turned on. Now what will happen? Why A is 0? A is connected. See, if A is 0, A bar B is 1, and how it is cross coupled, N1 transistor is off. That means N1 is grounded. I mean, N1 is turned on, A is grounded. So A is 0. So what happens when N2 is on? See, whatever, the static current or whatever the hanging of voltage value in bit line will be completely pulled down to ground through N2, A node and N1. Because N2 is on, N1 is on, right? So likewise, it will be, why N1 is on? Because A1 bar is 1. And at the same time, what will happen to the bit bar? N4 will also be turned on. N4 will also be turned on. And so whatever value is available in A, it will be passed to bit. As I said here, if it is 0, all the voltages from the bit line, it will be pulled down to N1. So bit value will be now 0, which is equal to A. So now we have completed the read operation. Similarly, for example, if it is 1 here, the same thing will occur. If it is 1 here, what will happen? If it is 1, N1 will be turned off, but P1 will be turned on. All right. So A will be pulled. This A node will be pulled up to what? VDD. So it is connected. So VDD is connected to bit via two transistors. One is P1, another one is N2. Both are on. This is how bit 1 will become 1. But you see in the timing diagram, we can see A is 0, but we get a bump. We can get a bump here from 200 picosecond to 400 picosecond. We are getting a bump. Why we are getting that bump? Because when A is 0, to our first case, when A is 0, what will happen? When we are putting bit and word line, bit is pre-charged and word is 1. So this N2 will be turned on. This N1 will be turned on. N1 is already on. That is why A is ground. Now N2 we are turning on the N2. So now what will happen if there are any hanging supply available in the bit line because of the pre-charge we did? That will make a path. Through where it will make a path? Through N2, through node A, through N1. It will make a path and it will reach the ground. That is why, so here we can consider as two resistance. One is because the resistance because of N2, another one is resistance because of N1. Right? Two resistors are in series. So that is why we have a supply, we have a bump of A, and again then it settles to what? Settles to 0, as it is already 0. So now you can see the bit bar, I mean the bit will be 1. Bit will be 1, because as I said, bit and bit bar both should be pre-charged. At the same time, what will happen in the bit bar side? Bit bar side, this will be turned on and this will be turned off. So bit bar will remain 1. Say bit is moving to 0, but bit bar will remain 1. Why? Because N3 is turned off, so it will not drain to ground. Rather, P2 is on, so now it will be pushed. So here, what are the things we need to consider? That is very important in designing 60 SRAM cell. It is very important to consider the sizing. Why? Because in read operation as well as in write operation, you see in the write operation and in the read operation, we are talking about the same feedback design, right? Same feedback design. And in the feedback design, see, at the same time, it has to switch. It has to flip. I mean, the cell has to flip from 0 to 1, or the cell has to flip from 1 to 0. Flipping means what? The connection, the node has to be connected with the ground through a transistor, or it has to be connected to the VDD through a transistor. If it is VDD, it will be through PMOS. If it is ground, it will be through NMOS. Am I right? So we have to make strong N2 and N4 comparing to P1 and P2. Why? Because say, for example, in the write operation, if we are putting 0 here, see, this N4 must be enough strong to pull this VDD. I mean, make this P2 to be turned off right at a minimum time, and this node must be converted to 0. Else it will not happen. So that is why N4 must be stronger than P2. So what is meant by stronger? What is meant by weaker? See, stronger means width will be larger than length of a transistor. So when W/L ratio is higher, we consider that as a stronger. So already we have discussed. I mean, the other sessions they have discussed about this sizing issues. So when we are talking about W/L, when width is higher, you get stronger. But in general, if you assume same W/L ratio of both PMOS and NMOS we are using here, especially for P2 and N4, say I'm assuming same W/L ratios for this P2 and N4. What will happen? N4 will be strong enough, because that is the beauty of NMOS, right? PMOS will always be weaker. NMOS will be stronger when we are having, even though we are having same W/L ratio. That is of other things. I don't want to go in detail about that. Similarly, in the left-hand side, you see for the A node, N2 must be greater than, N2 must be not greater than, N2 must be stronger than P. That means you can have same ratio, same W/L ratio. With the same W/L ratio, N2 will work stronger. But now, okay, that is a different case. Now coming to the read operation, we are reading whatever storing in the cell. So now what will be N1 and N3? The N1 and N3 should be stronger than N2 and N4. Then only A node can be maintained as 0. Because if we are having, if we are putting one here, I mean precharge here, and we are removing the precharge, we are removing the precharge pulse, and the bit line is now hanging. Say for example, this N1 is not strong. What will happen? This one, maybe that can be 1 or 0. If it is 1, it will make a as 1, but that is the inverse of read operation. See, we are going to read what is available in the cell, what is available in the memory cell to the bit line, but reverse is happening. Reverse will happen when N1 is not stronger. Similarly, N1 and N3 should be stronger. If it is not stronger, as I said, because of the pre-charge, that will replace, that will flip the value available in the node A and node A bar B. That should not happen. That is why I am telling sizing issue plays a major role in designing these kind of SRAMs. So coming to the sizing, SRAM sizing, as I said, what we should have? We should have a weak PMOS, we should have a medium NMOS, and we should have strong NMOS. Right? Then only it will maintain the A and A bar B values. So this must be weak, PMOS must be weak, and this NMOS, N2 and N4 will be stronger than the PMOS, and the N1 and N3 must be more stronger than the. So here, if we are going for simulation, even if the W by L ratio of these 4 devices, I mean this N2, P1, P2, and N4, all these things can be same. Considering NMOS is stronger than PMOS, so that will also work. But this NMOS should be more. I mean W by L ratio should be larger. That means width should be larger than length. All right, this is all about 60 SRAM. So as I said here, the other important case of this 60 RAM is considering the sense amplifier. So as I said, here we are having a weak signal, we are having a hang signal since during the read operation. During the write operation, we don't care because we are energizing the signal. We are energizing the cell to do what? To store whatever value we are giving in the bit and bit bar line in A and A bar respectively. But read operation, it's not like that. Read operation, say because of the static currents and the static power dissipation, in sometimes we are connecting VDD to the ground directly. I mean during the switching, both PMOS and NMOS will be on for a particular amount of time. So because of that, we have static power dissipation, right? So because of that, we may not have our full swing, full VDD we may not have in our bit. So that is why we are going for sense amplifier. This sense amplifier, so see, sense amplifier will not come as a off chip. Off chip means, see, memory separately and this sense amplifier separately we won't get. Usually the RAM cell is coming along with the sense amplifier. For example, if you are having 16 cells, we will be having 16 bits. We will be having 16 sense amplifier. To what? Simply to amplify the signal. So whatever we are taking from the bit lines, see here we are having a bit and bit bar lines. From this bit and bit bar lines, what we are going to do, we are connecting it here. Based on the topology, what we are doing, we can take the out. Right, so how we are enabling this amplifier? How we are enabling? See, it forms a kind of differential amplifier. So how it enables us here by using the sense amplifier enabled. So if you enable this one, this NMOS will be turned off. This PMOS will be turned on, right? Because it is a C bar active low. So what we will be getting, this PMOS will be enabled, this NMOS will be enabled. So obviously we will be having a doubt here. See what happens to the previously stored data. See here, again, we have to understand it very clearly. This works as an amplifier alone, even though it is similar to feedback connection, it is similar to latch. When we are energizing the circuit is the concept here. See, we are energizing the concept after putting the bit line values here and here. I mean, bit line and bit line bar values here. Then only we are enabling the SE. I mean, enabling this NMOS and enabling this PMOS. So the reverse operation will not happen. What is the reverse operation? Whatever value is available in the V out, it will not go back to the BL. I mean, bit line of the memory cell. See, that is memory cell. This is amplifier. For each memory cell, we will be having a sense amplifier. Only during the read operation, not for write operation. Okay. So what will happen? So we are putting the bit line when the bit line is connected here. Whatever the value is available in the bit line, that should be available as amplified output in the V out. The reverse should not happen. So how we are maintaining that? We are maintaining that by applying the signal, by applying the sense amplifier enable. after applying the bit lines to the sense amplifier. And this is another topology. So here, see, since we are talking about the static design, we have an advantage. What advantage we have? We can take the output according to our consideration. If we need to take V out, we can take. If we need to take out V out bar, we can take. That is the advantage of using these kind of static circuits. And again, this topology is also similar to not similar to, almost it is a differential amplifier that will sense the bit line, and it will energize and it will amplify the signal. And this is the use of sense amplifier. Again, here we have to understand a few things. In memory design, for write operation, sense amplifier is not required, because we are going to energize the cell individually. But during the read operation, to avoid the static currents because of the precharge, what we are going to do, we are going to attach a sense amplifier. And the sense amplifier is what? It is on chip. On chip means in the same memory cell, we will be getting the sense amplifier, right, as a package. We don't get, separately. See, you are getting the memory cell separately, and you are getting the sense amplifier as an off chip. Off chip means another chip, a separate chip. It is not like that. All the chips, all are on chip. The memory cell, the sense amplifier, all are on chip. Okay. So now coming to the DRAM, right? 3T DRAM. So here we are considering 3 transistors, and what makes its dynamic. So obviously we will be having a doubt. So when we are talking about dynamic, so we are not giving any clock pulse. How we are telling this as dynamic? See, it is not like that. Dynamic means there will be a capacitance. The capacitance can be parasitic, or the capacitance can be external. It can be parasitic or external. That needs to be refreshed again and again. That is why we have a name called DRAM. That doesn't mean we have to give clock signals. And in the static RAM, you compare the static RAM and dynamic RAM. In static RAM, we are having bit and bit bar lines. I mean, 2 separate rails, right? We call it as a double railing. In double railing, we will be giving bit line and bit bar line. But in dynamic RAM, it is not like that. You can see there will be two separate rails. One for input. BL1 is for input. BL2 for the output. And again, the word line also different. In static RAM, same word line will be used for read and write operation. But here it is not like that. See, for writing one word line, and reading we will be having another word line. So now how the circuit is connected, you see, we have an M1 and M1 NMOS, 3 NMOS transistors, M1 and M2 and M3. What about the CS? This CS, we can consider this as a stray capacitance, because that is a parasitic capacitance. That is not an external capacitance we are adding to the circuit. It is a parasitic capacitance. How comes the parasitic capacitance occur here or arise here? Because of the drain capacitance, and because of the gate capacitance. Drain capacitance of M1 transistor and gate capacitance of M2 transistor will form a stray capacitance. We call that as CS. And here we will be having a node M1. Say, okay, first we will go for write operation. So how we are writing it? So for writing it, we have to put the data. We have to put the data in the input line, which is BL1, and enabling a write word line. So I'm enabling this write word line. So now what will happen? This transistor, this blue line, the BL1 line is now 1. This M1 will be what? Will be activated. I mean, it will be turned on. So this 1 will be transmitted over here, because this acts as a switch. No? So yes. Okay. So the node X will be now 1. All right. So now you turn off the WWL. I mean, a write word line. So if I turn on this M1, right, X will be stay there itself. X will be staying there itself. Why it will stay there itself? Because this will not act as a switch now, because that is turned off. So the X will be turned off. The X will be maintained, and it will and how it will be maintained? It will be maintained because of the parasitic capacitance, because of M1 and M2. Drain capacitance of M1, gate capacitance of M2. Now you go for the read line. So that is how now you see the WWL and X. See, I am enabling the bit line 1, right? I am putting it 1, and I am enabling WW1. So when I make this as 1, what will happen to the X? X will be maintained at 1. You can see X will be maintained at 1. Why? Because the M1 transistor is now turned off, so that the charge stored in the X will not dissipate. It will not dissipate. Similarly, here it is a gate, so through this path also it will not dissipate. But this X can turn on the M2. That is the other thing we are going to do. We are going to see in the read side. So now we have seen the write side. You come to the read side. In the read side, what will happen? So now again I have to precharge it. So this will be precharge means again we have to do. It is not a precharge pulse. We have to maintain this BL2 as 1. So now I am maintaining this as 1. So and also I am giving the read pulse. So the M3 transistor will be turned on. Am I right? M3 transistor will be turned on. And now what will happen if this X is also turned on? So listen carefully. If here, according to our discussion, this X is 1 now, and it will turn on the M2 also. So now M3 will be turned on, M2 will be turned on. So what will happen to the BL2? Everything will be drained to the ground. So BL2 line will become 0. So accordingly, we will attach an inverter to say, 1 is stored. That is how we map. In the other case, let us assume if X is 0, what will happen to if it is 0? If it is 0 means M2 is not turned on. M2 is not turned on, but M3 is turned on, but M2 is not turned on. So the BL2 line will be maintained in 1. So inside, what is inside? Inside is X. What is red? Red is 1. You attach an inverter to see what is there in the cell. So this is how 3 transistor dynamic RAM work. So here there are no constraints on device ratios, and because the reads are non-destructive. Value stored at node X when writing at 1 is, you can see it will be minus of VT, and that is why you can see in BL2 when we are putting the read line, you can see a bump and then it is increasing. You can see a bump and then it is increasing because it will initially, when it is 1, it will make the M2 to be turned on. If it is turned on, charge will be drained to the ground, but X will not be completely 1. X is going to water. It is going to discharge. It is also a capacitance, right? It is going to discharge. So what will happen? So once it is discharged, again this BL2 will be pulled to 1. That is why we are seeing a bump in the from 1 to ground. We are having a bump in BL2 line. And the value of X will not be full VDD. It will be VDD minus VT. That's what we have studied in NMOS circuits. It will not pass completely. If you are giving a 2.5 volt, it will not pass complete 2.5 volt. It will pass 2.5 minus threshold voltage of the transistor, whatever it is available, depending upon the technology. Now coming to one transistor DRAM. See, in a static RAM we have seen 6 transistor. In dynamic RAM we have seen 3 transistor, and now we are seeing 1 transistor dynamic RAM. And here we don't have a concept of input bit line, output bit line, read word line, write word line. Here we don't have those concepts. But what we have we have only 1 transistor, and here we see this is not a stray capacitance. This is actually external capacitance. External capacitance means again it will come under the same package of the cell. It is not separate capacitance of the chip. It is on chip capacitance. So for example, we are putting 1 here and we are activating this WL. So this M1 will be M1 will be on. Whatever line we are putting, that will be stored under this CS. So during the read operation, here we are not going to precharge it. Precharge is not required here. Directly it can break. So when during the read operation, this WL will be turned on. When this is turned on, whatever value available in the CS, the capacitance, that will be available to this BL line. Again, we will be having bit line capacitance to drain that, to avoid hanging. So that's how 1T DRAM works. And we have several disadvantages of 1T. It requires sense amplifier for each bit line due to redistribution readout. And it is single-ended in contrast to SRAM. Single-ended means, you will be having, 1 bit line and 1 word line. But in static RAM, you can see we will be having bit and bit bar lines. It is here it is single-end. Then the readout of the 1 transistor DRAM cell is destructive. Read and reverse operations are necessary for correct operation. Why it is destructive means, see, once we are activating it for writing operation, we are activating the write line. For reading operation, we are activating the read line. Whatever the storage, whatever the energy stored in the CS, that will be appear in the bit line. We are not going to any. We are not going to do any switching or any major operation. We are going to do. So the unlike the 3T cell, 1T cell requires presence of extra capacitance that must be explicitly included in the design. See, the bit line capacitance, to drain out the hanging bit line after passing the value to the resistance, or after passing the value to the cell, or after taking the value from the cell. So then comes read-only memory, and read-only memory. How we will be having a read-only memory. That means, so now, as long as what we have seen, RAM kind of things. As long as the power supply is there, we will be we will be accessing, we will be doing the read operation, we will be doing the write operation according to our convenient we can do. But read-only memory is not like that, and because um, once it is programmed, it is programmed. So it will be available even though without the power supply. It comes under non-volatile. So here, how we are making the connection? Say we will be having several crisscrosses we will be having here, and at the same time, again, when we are talking about or discussing about a decoder, we must always keep in mind decoder output will be only one line, right? By selecting the appropriate input lines, we can select one line. For example, if we are selecting 3, how we are manipulating the bits, that is marked by connections. I'll show you in the next slide. You can see here. I am selecting, for example, I am giving 0, 0, 0, 1, 1. That means 3. So third line will be activated. For the third line, how we are denoting this X represents there is a connection. This X represents there is a connection between the vertical line as well as the horizontal line. So if it is X, that is considered to be 1. So what we will be having in A7 will be 1, A6 will be 0, A5 will be 1, A4 will be 1, A3 will be 0, and A2 0, A1 1, A0 0. Right. This is how this is like a permanent storage. So permanently it will be there. Permanently we can if this address is given, I mean if this third address is given, permanently it will consist of 10110010. This is the general concept. But how we are making the fuses? As I said, we will be having running 2 lines. One is horizontal line, another one is vertical line. Horizontal line and vertical line, how we are fusing it? We are fusing, there are different techniques we are going to see. First one is masking during metallization. This is a permanent fusing, right? You can see here, we have a level 1 and we have a level 2, and we have a concept called a via, and using that via, we will fuse the level 2 and level 1. So it is permanent, right? We cannot every now and then we cannot erase and rewrite. So once it is written, the data will be always available in the memory cell, right? Masking during metallization. And the next one, so what is the disadvantage of this masking? You see, for every design, for every memory cell, depending upon data, the entire masking process itself have to be done. See, I hope you know about the masking process. The masking process and how much cost is involved in that, and it is permanent. So once it is done, again that mask will not be used unless otherwise you get the same design. This is the disadvantage of masking during metallization, but that is why we go for fuse. In fuse also the same thing. Say you can see a horizontal and vertical lines, and that will be fused. That will be fused with thin layer. That will be fused with thin layer of metal. During fusing, what will suppose I don't want this connection? What I will be doing is I will be supplying high voltage, to burn out this fuse. We call that as PROM. We burn out this fuse. So once this is burned out, that will be considered as 0. All other places that will be considered as 1. So what is the difference between masking and this kind of fusing? Masking means for every design, we have to use individual mask. That impacts your cost. But in the fuse, it is not like that. You use the same mask, you manufacture this. Wherever I do not want the connection, wherever I want to fuse it, I can fuse it. So same mask for different applications. Here, individual mask for individual application. That is the difference between masking and fusing for PROM. So next case, EPROM. And in EPROM, what we have, it is like a normal operation of a MOSFET. So what is a normal operation? Say we will be giving a 5 volt, but instead of giving 5 volt, what we are going to give in the control gate, and again we have a polysilicon. So say this floating gate is a polysilicon. Why we call this as floating gate? Because that is not connected to any any terminal. It is we cannot connect to that terminal. It will be available. The polysilicon will be available inside. We don't deal with that. We don't connect with it. That is why we call it as a floating gate. The other things are same. How it is same? You see, instead of giving 5 volt to the control gate, you give 20 volts. You give 20 volts, right? Like higher volts you give. So what happened to the high voltage? If the supply is crossed, 2.5 or 2.75 volt beneath the gate, we will be having a formation of channel. Say for example, here we are giving 20 volt, here we are giving 5 volt, here we are giving source as 0 volt. So automatically what will happen? The electrons will be formed in the accumulator. The electrons will be accumulated in the channel beneath the gate. Now you increase the supply. Instead of giving 5 volt to the control gate, you increase this to 20 volt. So if you give 20 volt, what is the technique is happening? You see what is in general the length of the channel will be in nanometer in general, okay, or few nanometers. You agree with that? Few nanometers. We are giving what is electric field? Electric field is voltage applied over distance. So we are giving 20 volt over few nanometers. So huge electric field. The electric field will be very very high. You agree with that? The electric field will be very very high. So what will happen to the device? We call that as hot carrier effects. We call that as hot carrier effect because of that. High voltage applied over very less distance. That means high electric field. The electrons from the channel will be excited, will be pushed to the floating gate. Will be pushed to the floating gate, right? So it will be once it is pushed to the floating gate. Now even if you give 5 volt, the channel will not be formed. If the channel will not be formed, you consider that switch is not working. That is what we are doing in the previous case. Say for example, I do not want this connection. So what I am going to do, I am going to give higher supply, 20 volt supply. So the channel, the electrons available in the channel will be accumulated to the floating gate, to the polysilicon. So again, that will not go back. That will not go back to water. That will not go back to the channel. So even if you apply now 5 volt, the source and drain will not be getting connected here. That becomes non-operational. That the MOSFET become non-operational. Okay, now I want this to be operational again. What I can do? That is why I have a concept called, you can see in the kind of EPROM chips. In the top, you can see a glass, and we can pass the ultraviolet rays. What is the use of passing ultraviolet rays? So when you pass ultraviolet rays, the electrons available in the polysilicon gate, I mean the floating gate, will be excited now. The electrons will be excited now when you pass UV rays. On excitation, it will go back to what? It will go back to the drain. It will go back to the drain when drain is applied at 5 volt. This is what will happen in the EPROM. Erasable, programmable, read-only memory. And again, this is now become extinct. This is out of date now. So we are going for electrically erasable PROM. Electrically erasable. See, the same, under the same concept. I mean, the programming is same concept. How the programming is work? Programming means once programmed, the MOSFET will be considered as non-operational. That is programmable. So that is happening because of hot carrier effects. Agree. But here you see in the electrically erasable PROM, instead of giving ultraviolet rays, you give the supply itself to reverse the operation. How? Because here you can see the drain. Here you can see the floating gate. There is a small, curve-like thing towards the drain side. Why this has happened? You have studied the concept of tunneling. Tunneling means, a strip, a thin strip of electrons, pushing from drain region to the other region. Like when the MOSFET saturation, how it is, and the saturation means how it is happening. You can see the once the VGS is greater than VDS, what will happen? One side, in the drain side, the channel will be thinner. Thinner means how the electron will, it is because of tunneling effect, right? Because of the same tunneling effect from the polysilicon, the electrons will be pushed back to the drain. See, in the EPROM, we are using ultraviolet rays to do that. But in electrically erasable PROM, by using tunneling effect, we are making only by giving the electrical signals, not UV. Only by giving the supply, we are doing it. This is EEPROM. All right. So this is these are all the things we can go for programming a ROM. Programming a ROM. All right. So we will continue this MOS R ROM in a minute. Give me a minute. Okay. Okay, my screen is visible, right?
Yes, sir.
Yes. Okay. So now coming to the R room, mass R room. Say that these are all simple concept, and based on the topology, we are getting the name. I'll tell how. See, for example, here. So see, first we have to assume that, not assume. Actually, what will happen is in all the lines, you can see in all the crisscross. In all the crisscross, we will be having the transistor, and we are programming the transistor to be non-operational. Right, that is what we are doing here. So we have not programmed only the 5 transistors here. See how we are having a VDD line. For the next 2 lines, we are having another VDD line. Right, VDD line we are having, not ground, VDD. And from where this we will be getting the word lines? Word lines we will be getting from decoder, that we know. And we are having the bit lines. And in the bottom we have pull down loads. This is very weak pull down. Why this should be very weak? I will tell you. This is pull down. Pull down means always this will be turned on. Right? Always this will be turned on. That means what will be the value in the bit line? Bit line value will be 0. Similarly, bit line 1, the value will be 0, 0, 0. Bit line 0, 1, 2, 3, everything it will be 0 because it is a weak pull down. Why it should be weak? That I will tell. So now you come to the WL0. In WL0, for example, if you are giving 1, what will happen to this transistor? This transistor will be turned on. If this is turned on, what will happen? If this is turned on, this VDD, this VDD will be, this VDD will be available. This VDD will be readily available to here, 1. But you remember, the same line is pulling to ground. That is why we should get this as a weak pull down device. So this VDD will now be available here. So in the first line, what is the memory we will be seeing? This is 0, this is 1, this is 0, this is 0. Am I right? Similarly, in the second line, you see VDD is connected to this. So if this is 1, through this, the VDD will be available here. That is 1. Here, no device, 0, 0, 1. And the third case, 0, 1, 0, 1. Fourth case, 0, 0, 0, 0. All right. Okay. This is a simple thing only. Then why the name comes like R? Because you can see here, WL0 and WL2, we are having 2 transistors in the same bit line. Whether these 2 transistors can be turned down at the same time? Never. Why never? Because since the word lines are coming from the decoder, any one of the word line will be activated at a time. Right? Either this transistor will be activated or this transistor. This should be the doubt we should have here. Right, since this is a output from a decoder will always be having only one watt, only one output line. Right. See, I am talking about in general operation of decoder. We have, the active low decoder also. In that only one will be turned off, other lines will be turned on. That is also we are going to see the next. So here we will be having 0, 1, 0, 0. And you can see the 2 NMOS transistors are in series. So which is like an R condition. That is why the nomenclature we call that as R RAM, nothing other than that. This is R room. Now coming to the NOR room, again we are having the same word lines. See, in the R room we are having VDD lines running here and there. Say for every 2 word lines we are having VDD lines. But here we are having ground lines. That means it is by default it will be 1. And you can see in the previous R room we have used to pull down devices to make the line as 0. But here we are making a grounded PMOS. What is meant by grounded PMOS? That means the PMOS will be always on. That means the line will be given always with 1. Say that here it will be 1, 1, 1, 1, 1, 1, 1, 1. Like that it will be there. But we are making a transistor to turn that off. See, if I'm making this transistor to be 1, I mean, if I give WL3 as 1, this transistor will be turned on. If this is turned on, you can see ground will be connected to this line. See, again, we should have a doubt here. Sir, already here we are having VDD is connected to this line, and again, our ground is connected. What will happen? Certainly, we will be having static power dissipation. Certainly, we will be having static current flowing because of that static power. These are all, see, even though we are having some disadvantages, this topology works fine for our memory. That is why we are using, right? Okay. So now what will be the logic based here? So here we will be having 0, 0, 1, 0. Right? 0, 1, 0, 0, 0, 1, 1, 0. 0, 0, 1, 1. Likewise, we will be having a NOR room. What is the difference between R and NOR? R means, pull down loads will be always be there. Wherever you don't have transistor, there it is 0. You don't remember like that, but you understand how it works. But in NOR ROM, it is different. All the lines will be pulled to 1. We are making a transistor turned on to connect that with ground. That is NOR. And another one case is NAND. See here, as I said, we are going to use active low decoder. In active low decoder, you see, but what is the general operation of decoder? You can see here at any point of time, only one line will be 0. For example, if you are giving 0, 0, only 0 will be 0. All other things will be 1. And also all other things are connected to pull up devices. So that means BL3, BL2, BL1, BL0, everything will be 1. All right. But we are making the connection to become 0 by using, the devices. Since it is like a series connection, we are calling that as NAND. So wherever we are having, thing, we consider that as 0. All other things are considered to be 1. This is how NAND ROM works. So as I said, we have the static power dissipation because of, we are having the ground and VDD are in contact sometimes. What we are having static current dissipation. Because of that, we have static power dissipation. So to avoid that, we are going for pre-charging the devices. Pre-charge operation. Pre-charge means, see, again, we are giving only the pulse. We are giving only the pulse. And based on that, we will be having it. If it is on, it will be connected to the VDD. If it is off, it will not be connected to the VDD. And we can have the ground lines are connected, so making it as ground. So we will be having 1. If we have the transistor to turn on, that will be considered as 0. That will be considered as 0 in the other cases. So we will be having a 0, sorry, 1, 0, 1, 1, like that we will be having. This is pre-charged mass not. So now coming to the row decoders, as decoder plays a major role in memory design. So for example, we need to have since we are talking about 8-bit decoder, so how many things 2 power 8 we need? So 256 NAND gate we need. For example, I need to make this as 1. Say I have to give, say, for inverter, I mean the bar inputs, we need 8 inverters. Say A7 to A0 we have. Similarly, A7 bar to A0 bar, we need inverters. So based on that, we will be having the decoders. And here we will be having, I will just give the important things about the row decoder. Since we are having 8 input to a gate, obviously we have studied in combinational circuits what disadvantage we have. We have large fan-in. Because of large fan-in, we will be having delays, and again how it affects our output, how it affects our performance, we have seen. So we do not want that, but so that is why we are going for grouping of devices. Say for every, say here you can see A0 and A1, here A2 and A3. Similarly, I will be having A4 and A5, then A6 and A7. Like this, I will be having 256 NAND gates. Instead of driving a NAND gate by 8 input, we are driving that by 4 inputs. See, somehow we are giving some, considering the large fan-in problem. But we are not going to decrease number of NAND gates. Number of NAND gates remain 256. So again, this is how the decoder works, right? By using the pre-charge devices, and this one is NOR decoder. And in NOR decoder, how it works, you can see when A0 and A1 is 0. For example, if A0 and A1 first 2 bits are 0, 0, say these transistors will be turned off. For example, you consider only this line. You consider only this line. Say what will happen? This will be turned off. This will be turned off. So it will not be connected. It will not be connected. This line will not be connected to what? VDD. So for all other options, it will be only, only when A0 and A1 is 1, these 2 transistors will be turned on. All other cases, it will not be turned. This is how the row decoders work. Whereas in NAND decoder, it works in a similar way, but here we are giving to supply NAND, we are giving to the ground. Right, pre-charge we give here, to enable the devices. There is a difference between NOR and NAND decoder. So other type of decoders are also here. See, as we have seen, we have large fan-in problems, we have delay problems, and of course we have area problem, because you see 256 NAND gate for each decoder we are giving 256. NAND gates. So to avoid that, we are going for a column-based, I mean tree-based column decoder. Here, what will happen? Here, say for example, A0 and A1 is 0. A0 and A1 0 means this transistor will be turned off, this transistor will be turned off. All other remaining transistors will be turned on. So bitline 0 will be connected to D by, this transistor will be on and this will be turned on, this will be connected to here. Similarly, if for example, all other operations, say at any point of time, the lines will be connected to D, like it will find an alternate path. That is the beauty of this tree-based column decoder. Here we are decreasing the area, we are decreasing the number of transistors, but at the same time, delay is hugely increased. Why hugely increased? Because it finds an alternative way to push to the supplier ground, right? I mean to the data line. So that is why here we have delay. Even though the number of devices, I mean the area is decreased, obviously we will be having the delay. Now coming to the flash storage. So flash storage, we have seen many examples in day-to-day life. We are using from pen drives to external hard disk, and mostly it is based on NAND and NOR type. One is NAND and another one is a NOR type. So NOR is byte addressed and NAND is page addressed. I don't want to get in detail about the addressing, page addressing and byte addressing. That anyway, we will just I'll just give you the thing. How the NOR flash and the NAND flash is working, it is again based on the two operations. I mean, by floating it and by using the tunneling. The same thing here it works. And then during the programming, during the programming of a device, what we are doing hot carrier effects. Similarly, for erasing, we are doing the tunneling. NOR flash, you can see we will be we'll be having the bit line and source line are getting connected over the device. When the device is turned on, the bit line and source line will be getting connected. But in the NAND also it works in the same way. But how the topology is, you see, we have a bit line select, to select the word line, individual memory cell, and that can be connected to the NAND flash. See, NOR. See, the basic idea is NOR comes in parallel manner, NAND comes in series manner. Say when we have seen the inverter design itself, making a 2-input NAND gate is easy comparing to NOR. We have NOR designing NOR cells. It goes in parallel. One memory cell will be in parallel with other things. That is why it is fast, but it is more expensive because when we are going for labs for developing the chips, it will be costly. But in the NAND, it is of serial. Of course, the fabrication and layouting principles are simple. Not simple means considerably simple than NOR. So NAND has higher memory capacity. This is how the same thing. I don't want to discuss more on this. Can skip this. So finally, content addressable memory. So here, as I said, usually we address the memory by the address lines. That's what we do, whether it is in random access or non-random access, we do. But content addressable memory is not for those kind of applications. Where we will be using content addressable memory, especially in network, because in networks, see, for example, I have connected with some 2 or 3 devices, 2 or 3 devices through IP address I will connect, and I know what data is to be getting from what device. What data I have to connect with what device. So there, without calling or without referencing that using the identity, I mean the address, I will directly use the content, because I know where is the location of the content. So I will directly address it. Particularly in networking kind of applications, we use this kind of content addressable memory architectures. This is as usual it will work. But the thing is, we are just checking what data is it. So you can see the architecture here. Say we have a word line and bit bar lines. Say we are having a match signal. For example, we are giving this bit line as 1 and bit bar is 0. For example, if in the cell, for example, if it is 1, it will be 1 if this cell bar is 0. And again, by using the feedback coupled, we are having these two transistors, NMOS transistors to be turned on, that can be referred with, cell line and the match line. So whatever is available in the match line, that will be reflected in the cell. Whatever is available in the cell, that will be available in the match because of the feedback. By using, cross-coupled inverters. Cross-coupled inverters, we are maintaining this. So it is a 10T cam cell. You can see we are having 1, 2, 3, 4, 5, 6, and 2 transistors in the inverter. So totally we will be having 10 transistors. And for reading and writing, it is like an ordinary RAM. It can be accessed by row decoder and column decoder. But the thing is, we know the content. We know what is the content. Accordingly, we use by using the miss and match lines. Miss means it is inversion of match. So whatever is matched in the content, that can be directly accessed by the match without by knowing its address. So this is how the content addressable memory works. So with this, I'm winding up my lecture. Any questions or any discussions? I'm happy to have. And you can have your, you can have my mail ID and contact. If you have any doubts, you can always mail or call.
Okay, sir.
Thank you very much, participants, for your patience. I thank Kartika ma'am. I thank the other coordinator, Ramesh sir. I thank Manju ma'am for the opportunity given to me. Hope the session were fruitful to all of you. Please let me know if you have any doubts here or through the mail or phone. Thank you for the opportunity, ma'am.
Thank you, sir. Thank you, sir. Sir, on behalf of Department of ECE, MSAGCE, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this FTP on VLSI and chip design organized by our institution. I thank our resource person, Dr. Konguvel, sir. This is very informative session, sir. Hope this session will be useful for our faculties and participants. We are really enlightened with your knowledge and presence, sir. We are thankful to our management for their motivation. I would like to thank our principal sir and HOD ma'am for their enthusiastic support. A special thanks to our organizing committee, teaching and non-teaching staff for their unflinching support and coordination. Last but not least, our heartfelt thanks to our participants. So with these warm words, we move to the end of this session. Thank you, sir. The next session will start sharply by 2 p.m.
Thank you, ma'am. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.